There's this one puzzle in cosmology that's been bugging scientists for decades. It's really one of the biggest questions out there. And my own search for an answer, well, it took me somewhere completely different. It led me to this new idea I call the Dilational Flooding Model. So let's dive in and see what that's all about.
Okay, so here's the mystery in a nutshell. When you look at these beautiful spiral galaxies, the stars way out on the edges are just whipping around. They're moving so incredibly fast that they should, by all rights, just fly right off into the void. It's like spinning a weight on a string, and the string just isn't strong enough. The gravity from everything we can actually see, all the stars, the gas, the dust, it just doesn't add up. It's not nearly enough to keep those galaxies together. So what is going on?
Right, so for a long time, there have been basically two big ideas on the table. The first, which is kind of the standard answer, is something called dark matter. The idea is there's this invisible, mysterious stuff all over the place that gives us the extra gravity we need. Simple enough. Then there's another camp, a leading alternative called MOND, that says, whoa, hold on. Maybe we don't need new stuff. Maybe gravity itself just works differently when things are moving really, really slowly. Now, both of these are really clever ideas, but let's be honest, they both got some issues that just won't go away.
And that's where I kind of hit a wall and started thinking, okay, but what if both of these camps are missing the bigger picture? What if the answer isn't about finding new particles or rewriting the laws of physics? What if it's something to do with time itself, an effect that's built up over the entire history of the cosmos? That's the seed, the core idea, behind what I call the Dilational Flooding Model, or DFM for short.
So DFM kicks off with a pretty bold claim, I'll admit. It says the universe isn't actually expanding at all. Instead, picture it as this huge static space. And all those effects we think are from expansion, like the light from distant galaxies getting stretched out and looking redder, that's not from space stretching. It's from time stretching. It's the cumulative effect of time dilation, building up over billions and billions of years. Basically, our entire view of the cosmos is being filtered through this incredible deep time lens.
I've named this central idea dilational flooding. Here's the way to think about it. Imagine the vacuum of space isn't truly empty. Think of it more like a sponge. And over cosmic history, the sponge has just been soaking up time dilation. It's become completely saturated. And once it's saturated, it actually changes the properties of space itself. It starts to create this extra gravitational pull that grabs onto stars and bends light, doing exactly the job we invented dark matter for. Okay, but a cool-sounding idea is one thing, right? The real acid test for any scientific model is, can it make predictions we can actually go out and test? Does it match the real world? So that was step one. I took the DFM framework and I pointed it at a classic, well-known galaxy called NGC 3198 to see if the numbers would actually work. And the calculation itself is surprisingly straightforward. It goes like this. First, you figure out how old the galaxy was when the light we see today left it. For NGC 3198, that's about 12.95 billion years. Now, in this model, that age is key because it tells you how long the light has been traveling and accumulating time dilation. So we treat it like an effective distance. Then you just take the good old Hubble constant, which we already have, and you use it to find the total amount of dilation. And boom, that one factor directly tells you what the acceleration on those outer stars should be. No extra knobs to turn. So you run the numbers through the DFM equations for this specific galaxy, NGC 3198, and this is what you get. An effective acceleration of 1.21 times 10 to the negative 10 meters per second squared. Now, if you're familiar with MOND, that number should ring a bell, because it's an exact match for MOND's fundamental constant, A0. But, and this is the absolute key, this is where the two models diverge completely. In MOND, that number is basically a fudge factor. It's a constant they plug into the equations because it makes them fit the data. In my model, DFM, this value isn't plugged in. It's predicted. It falls right out of the universe's age and the Hubble constant. It's not a fix, it's a consequence. So, okay, if both models can land on the same number for this one galaxy, you might be asking, what's the big deal? What's the real difference here? Well, this is where it gets really interesting and where DFM, I think, really shows its strength by giving a much deeper explanation. The difference is actually huge. See, in my model, this whole dark matter effect is something that evolves. It builds up over cosmic time as space gets more and more saturated. That means a young galaxy should show less of this effect than an old galaxy. MOND is totally different. It's a static law. It says gravity just works this way, period. It's always worked this way from the beginning of time, and it doesn't care one bit how old a galaxy is.
And this is what makes it so exciting. It gives us clear, testable predictions, as you can see here. DFM says that the flatness of a galaxy's spin should get more extreme as it gets older. MOND says it should be the same for all galaxies, no matter their age. So what does that mean? It means if we look way, way back in time at very young galaxies, what astronomers call high redshift galaxies, DFM says they should look more normal, more Newtonian. MOND says they should look exactly like the galaxies right next door.
And that right there, that is the single most powerful prediction of the dilational flooding model. And what's great about it is that it's falsifiable. That's science. It means you can prove it wrong. All we have to do is use our amazing new telescopes, like the JWST, to look back in time and see what those ancient galaxies are actually doing. We can finally put these two ideas head to head.
So let's be crystal clear about what we're looking for. My model, DFM, predicts that the further back in time we look, the weaker this dark matter effect should get. Those really early young galaxies, they should be spinning pretty much exactly how Isaac Newton would expect. MOND, on the other hand, predicts we'll see no change at all. It's a clear fork in the road. They can't both be right.
But here's where things get really exciting. This whole idea might actually solve another huge puzzle that's been giving astronomers headaches lately. You've probably heard about it, the impossible early galaxy problem from the James Webb Telescope. JWST is seeing these huge, well-formed, mature galaxies so early in the universe that, according to our standard theories, they just shouldn't exist. They didn't have enough time to grow that big. Well, it turns out DFM offers a surprisingly simple solution.
Remember how I said DFM is based on a static, non-expanding universe? Well, a consequence of that is that it calculates distances differently. It predicts that these very distant, high redshift galaxies are actually closer to us than we thought. And if they're closer, their light didn't have to travel for quite as long to reach us. And if the light didn't travel as long, that means the galaxies themselves are older than we assumed. They're not impossibly mature at all. They had plenty of time to evolve. The whole problem just vanishes.
So it all leaves us with this one big, kind of provocative thought. For the last 50 years, we've been on this massive hunt for a mysterious new particle, for some new law of physics to explain how the universe works. But what if we've been looking in the wrong place? What if the secret wasn't hidden in some new form of matter at all, but was instead woven into the very fabric of time itself, building up, second by second, over billions of years?